Tonight, the journey begins at the edge of everything familiar, beyond the planets, beyond the fading warmth of the sun. Two small spacecraft continue into the darkness, carrying the memory of Earth farther than anything humanity has ever sent before. Voyager is not only a mission of science, it is a slow passage into the unknown, across giant storms, frozen moons, hidden oceans, and the invisible boundary where the solar system gives way to interstellar space. Before beginning, a quiet thank you goes to everyone listening tonight. If this is the kind of deep space journey worth returning to, please take a moment to like the video, subscribe to the channel, and share it with someone who loves astronomy, mystery, and the long silence of the cosmos. It truly helps the channel grow. It would also be lovely to know where this journey is reaching tonight. Please leave a comment with the time and the place from which this is playing. Now, with the lights low and the stars waiting in the distance, it is time to begin the incredible journey of Voyager beyond the solar system. Long before the Voyagers drift beyond the last stronghold of sunlight, before they touch the thin and difficult boundary where the sun begins to lose its grip, their story begins in a place of pressure, heat, and careful measurement. It begins on Earth, in rooms full of diagrams, vibration tests, thermal chambers, and patient calculations, where engineers and mission planners try to imagine conditions no human body can endure. Space is already known to be severe close to home. It burns and freezes with little warning. It strips surfaces with radiation. It offers no air, no shelter, and no softness of any kind. Yet by the middle of the 1970s, this severe emptiness presents a rare invitation. The giant planets are moving into an arrangement that happens only once in many lifetimes. Jupiter, Saturn, Uranus, and Neptune are lining up in such a way that one spacecraft, if guided with great care, might use the gravity of one world after another like a chain of silent slings. A machine could be thrown outward faster than any rocket alone could send it. A narrow opportunity opens inside a vast indifference. That opportunity shapes the Voyager mission. The idea is elegant in outline and unforgiving in practice. A spacecraft leaves Earth, crosses the inner darkness between the planets, and arrives at Jupiter, moving quickly but not quickly enough. Then Jupiter itself, through its immense gravity and its own motion around the Sun, bends the path of the spacecraft and lends it extra speed. Saturn can do the same. Farther out, if timing remains exact and if the machine survives. Uranus and Neptune may also become stepping stones. The method is called gravity assist. Though the phrase sounds gentler than the reality, nothing is being assisted in any ordinary sense. The spacecraft falls toward a giant world at enormous speed, threads a path through a region crowded with radiation, rings, moons, and invisible hazards, then escapes on a new course. A tiny error early in the flight can become a vast miss later on. Success depends on a form of patience that borders on audacity. Two spacecraft are built because one is not enough. Redundancy is part caution and part ambition. Each probe is fitted with cameras, spectrometers, magnetometers, detectors for charged particles, instruments for plasma, instruments for radio science, and systems designed to keep working in temperatures and lighting conditions that change beyond ordinary experience. They carry dish antennas wide enough to whisper across billions of kilometers. They carry power sources that do not rely on sunlight, because sunlight weakens too much in the outer solar system. Instead, they draw steady heat from decaying radioactive material and turn that heat into electricity. It is a quiet form of endurance, one that suits the mission. The spacecraft are not fast because they are strong. They are fast because they are precise. They also carry something less practical and more difficult to define. Fixed to their bodies are golden records, carefully prepared discs containing sounds, music, greetings, and images from Earth. In strict engineering terms, these records do nothing. They do not help steer the probe. They do not protect an instrument. They do not extend the mission by a single hour. Yet they remain attached all the same, as if the mission cannot leave home without carrying some token of origin. The gesture is modest and strangely uncertain. No one expects a reply. No one can say whether these records will ever be found, or whether the idea of being found has meaning in the depth of time ahead. Still, the records go. The machines are built for measurement, but they also carry a hint of testimony. Voyager 2 leaves Earth first, in late August of the year 1977. Voyager 1 follows in early September, though its name suggests the reverse. The numbering reflects encounter sequence rather than launch order, because Voyager 1 is set on the faster path to Jupiter and Saturn. The launches are moments of bright force, but brightness lasts only briefly. Once the rockets have done their work and the upper stages have released their cargo, the probes become small moving points, then radio signals, then abstractions on tracking screens. Their real environment is no longer the launch pad or the sky above Florida, but a widening volume of darkness where no repair crew can travel. Almost at once, every ordinary failure becomes extraordinary. A stuck mechanism, a drifting sensor, a problem in memory, a fault in attitude control. Any one of these can grow into a permanent condition. A spacecraft far from Earth does not recover in the human sense. It either continues with damage, or it falls silent, even near Earth. The silence around it is deceptive. Space does not remain empty for long once instruments begin to read it closely. The probes pass through the region shaped by solar wind, the stream of charged particles flowing outward from the sun. They monitor magnetic fields that curve and twist through interplanetary space. They sense particles accelerated by storms on the sun, already before the first giant planet has grown large in the cameras. The mission is discovering that the solar system is not a set of isolated worlds hanging in stillness. It is a moving medium. It breathes, though not with air. It flickers with invisible structure. Distance does not thin it into simplicity. Distance reveals more layers. As the Voyagers move outward, they approach a place long familiar in telescopes and mythology, yet almost unknown in detail. Jupiter appears first as a bright object among stars, then as a disk, then as a whirl that expands too quickly for comfort. Its pull reaches far beyond the visible planet, its magnetosphere. The region controlled by its magnetic field is immense. Its radiation belts are fierce enough to threaten delicate electronics. Around it circle moons that from Earth have seemed like points of light for centuries. The mission is planned with care, but planning alone cannot remove uncertainty, because many of the actual conditions are still only partly known. A thin ring, if present and misplaced in expectation, can become a danger. A radiation level slightly above prediction can shorten instrument life. A moon thought to be cold and inactive may prove otherwise. The outer solar system has been seen, but it has not yet been met. That difference between seeing and meeting slowly becomes the emotional center of the journey. Telescopes offer shape, color, orbit, and brightness. A passing spacecraft offers nearness, and nearness alters everything. Features separate from blur, surfaces reveal scars, fractures, clouds, and unexpected textures. Atmospheres show layers where only haze had been assumed. Magnetic fields prove stronger or stranger than expected. Even time begins to behave differently. Events that once seemed static are found to be changing from hour to hour. A storm moves, a plume rises, a moon turns, a shadow crosses a cloud deck. The giant planets are not remote ornaments. They are active systems, each with its own rhythm and instability. The deeper mystery is quieter. These machines are leaving the region in which human attention usually stays anchored. Earth grows smaller behind them, and with that shrinking comes a change in scale that is hard to hold in the mind. The moon becomes irrelevant. Mars becomes a passing inward memory. The asteroid belt, once imagined as a major divide, becomes only another cross distance. Ahead lies Jupiter, then Saturn, then perhaps worlds that no spacecraft has ever seen at close range. Beyond them lies a darker thought. If the gravity assists work too well, if the instruments survive too long, if the power decays slowly enough, the probes will not merely visit the outer planets. They will continue outward for centuries, then millennia, carrying dwindling heat and fading intention into regions where the sun becomes just another bright star among many. For the moment, though, everything narrows to approach. The Voyagers remain machines of discipline, turning gently to keep antennas aligned, instruments sheltered, cameras prepared. On Earth, teams wait for signals that arrive after long delays and speak in patterns of data rather than in scenes. Outward from Earth, the spacecraft falls steadily toward the first giant gate. Nothing in their design suggests drama. They are compact, methodical, and almost plain in appearance. Yet the path ahead leads towards storms large enough to swallow planets, moons that burn, rings made of ice and ruin, and boundaries where the sun itself begins to thin. The mission starts as engineering. It already begins to feel like trespass into a place that has been patient for billions of years, and is only now being disturbed by two small objects carrying the weight of a distant world. Jupiter does not reveal itself all at once. For a long time it is only a destination attached to numbers, radio schedules, correction burns, and the slow discipline of navigation. Then, as Voyager closes the distance, the planet begins to dominate not just the camera frames but the logic of the journey itself. Nothing this large can be approached casually. Jupiter is the most massive planet in the solar system, a world so heavy that it has shaped the architecture around it for ages, tugging comets, disturbing asteroids, and holding a court of moons that seem almost like a smaller system of their own. From far away it appears smooth, striped, and calm, a polished globe banded in cream, rust, and muted gold. Up close, that calm becomes an illusion. Its cloud tops are restless. Belts and zones wrap around the planet in parallel streams moving at different speeds. Storms open and shear apart. Vortices spin beside one another for weeks, years, perhaps far longer. What had seemed like stable decoration from Earth is revealed as weather on a scale difficult to absorb. The Great Red Spot is one of the first features to force a change in perspective. Telescopes on Earth have watched it for centuries, and already it is known as a giant storm. Voyager shows more than its shape. It shows its structure, its layered edges, its surrounding turbulence, and the sense that it is not painted on the atmosphere but deeply embedded within it. It turns inside a broader field of moving cloud bands, its reddish colour changing in tone, its margins roughened by smaller disturbances. It is not still for the camera. It is alive in the slow planetary sense, a circulation vast enough to hold more than one Earth across its breadth. Yet even this famous storm is only one part of a much larger instability. Around it are white ovals, brown barges, knots, streaks, and waves. Each marking flows and eddies inside an atmosphere with no solid ground near the visible surface. The eye looks for continents or coastlines and finds none. Jupiter offers motion without land, shape without a surface that can be reached and stood upon. The very idea of weather seems altered here. There is no calm beneath the clouds to complete the picture. There are only deeper layers, rising pressure, strange chemistry, and eventually conditions under which familiar matter begins to behave in unfamiliar ways. As the data returns to Earth, Jupiter grows less legible and more compelling. The planet emits more heat than it receives from the Sun. That fact is already suspected before Voyager, but the mission helps confirm just how active the giant really is. Deep inside, energy is still moving outward, leftovers of formation and slow contraction adding their influence to the atmosphere above. Jupiter is not merely illuminated from outside, it is active from within. This internal heat helps explain the violence and persistence of its meteorology, yet explanation does not entirely reduce the sense of strangeness. A storm lasting centuries, a planet radiating excess heat, cloud systems arranged like a grand order yet constantly breaking into turbulence. All of this suggests a world balanced not in calm but in perpetual unrest. Its magnetic environment is even more unsettling. Jupiter possesses an enormous magnetic field, and the region it controls stretches across an immense volume of space. Charged particles become trapped there and accelerated. Radiation belts form, harsh enough to threaten instruments and distort expectations. Voyager enters not only the vicinity of a planet, but the influence of an invisible system surrounding it. Instruments detect waves, particles, and fields that do not show themselves in visible light. Space near Jupiter is not empty and passive. It is electrically alive. For the mission teams, this creates practical concern, because every hour near the giant world must be managed against the possibility of damage. For the unfolding narrative of the journey, it creates something else. The first giant planet is no longer just a destination, it is a threshold. It demonstrates that outer space, even far from the Sun, can be more intense than the region nearer Earth. Then a quieter surprise appears. Jupiter has rings. They are faint, delicate, and very unlike the bright and broad rings that later become inseparable from Saturn in the imagination. Yet their discovery matters. A planet long observed, studied, and admired still holds a feature unseen until a spacecraft passes close enough under the right lighting conditions. The rings are thin and dusty, almost ghostly, easy to miss and difficult to love at first glance. But their presence changes the sense of completion that telescopic astronomy often suggests. If Jupiter can hide rings in plain view, then the solar system may be less fully known than it appears. Familiarity becomes a weakness. Distance had encouraged confidence. Nearness begins to correct it. The largest corrections come from the moons. For centuries they have been points of light, orderly companions following predictable paths. Their motions help prove the structure of the cosmos. Their individual natures remain largely obscure. Voyager approaches them one by one, and the tidy concept of moons as minor worlds begins to fracture. Ganymede is found to be immense, larger than the planet Mercury, with a complex surface marked by both old impact scars and strange grooved terrain that hints at deep internal history. Callisto appears dark, ancient, and densely cratered, preserving the memory of countless collisions. Europa reflects light from a bright icy shell crossed by long lines and cracks, offering the first strong visual hint that its exterior may not be the whole story. Even before later missions deepen this idea, Europa begins to look like a locked surface under which something once moved, or may still move. But it is Io that breaks expectation most completely. Nothing in the old image of a moon prepares the mind for what Voyager sees there. Its surface is not dominated by the familiar language of impact craters. Instead, it appears mottled in yellows, oranges, reds, blacks, and pale patches, a world stained rather than weathered, chemically vivid rather than quietly grey. And then, in one of the most startling moments in planetary exploration, active plumes are detected rising from the surface. These are not fossil traces from a distant age. They are eruptions in progress. Material is being thrown upward into space. Volcanoes are active on another world, and not merely active in a modest sense. Io is violently alive. The plumes reach great heights. The surface seems to renew itself so often that old impact scars cannot accumulate in the ordinary way. A moon that should, by older expectations, be cold and inert is instead the most volcanically active body known in the solar system. This discovery shifts the tone of the mission. Until this point, outer worlds can still be imagined as colder versions of familiar planetary history, places where activity has slowed and ancient forms have endured. Io offers the opposite. It is a place of ongoing upheaval, heated by tidal forces as Jupiter and the neighbouring moons pull and flex it from within. Here the source of internal energy is not only leftover warmth or radioactive decay, but continuous distortion. Gravity transformed into heat through motion and resistance. The result is a world kept unstable by its very place in the Jovian system. Orbit becomes torment. Repetition becomes fire. A moon can burn not because it is large, but because it is trapped in a precise dynamical relationship that never lets it settle. The discovery is scientific, but its emotional effect is harder to separate from wonder. A body circling far from the sun, in a region once imagined as cold and increasingly dead, turns out to be erupting so powerfully that its material helps feed a cloud around Jupiter. The giant planet and its moon are not merely neighbours. They exchange influence continuously. Particles from Io contribute to the larger environment. Radiation shapes surfaces. Gravity drives internal heat. The Jovian system begins to look less like a planet with attendants, and more like a whole interacting organism of fields, tides, dust, ice, and energy. Voyager also records details of Jupiter's smaller moons, its auroral processes, and the fine structure in its atmosphere and surroundings. But the larger pattern is now unavoidable. Every closer look increases complexity. Every answer widens the frame and lets new uncertainties in. Jupiter is not only a destination successfully reached, it is proof that the outer solar system is not a quiet archive of frozen leftovers. It is dynamic, layered, and in some places unexpectedly violent. The first giant world has not simply been photographed. It has overturned assumptions. It has shown that planets can hide rings, that moons can behave like active planets, that invisible fields can dominate huge regions of space, and that distance from the sun does not guarantee stillness. When Voyager leaves Jupiter behind, it does not depart unchanged, and neither does the story. The gravity of the giant world bends the spacecraft onto a new path and lends it speed, just as mission planners intend. Yet Jupiter has done something less measurable as well. It has established a pattern that will continue outward. The farther the probe travels from Earth, the less the solar system resembles the neat model carried in from textbooks and telescope images. Structures turn out to be temporary, surfaces turn out to be active, worlds turn out to conceal processes that only nearness can reveal. Ahead lies Saturn, ringed and luminous, often imagined as the most serene of planets. After Jupiter, serenity can no longer be trusted at first sight. Io draws the gaze back even after Jupiter has filled the frame with storms and force, because there is something almost unreasonable about it. A moon in the outer solar system is expected to preserve the old silence of formation. It is expected to be cratered, dim, and largely spent, carrying on its surface the record of impacts and little else. Io refuses this role so completely that it seems, at first, to challenge the logic used to describe such bodies at all. It circles close to Jupiter, deep inside the great planet's field of influence, and from a distance it appears small, bright, and manageable. One more companion in a crowded system. Yet the closer instruments look, the less it resembles a moon in the ordinary sense. It becomes a place of continual renewal, a world that erases its own past almost as quickly as it makes it. Its size is modest compared with the great planets, but not trivial. It is slightly larger than Earth's moon, and more massive than the moon by a noticeable margin, which already hints at a denser internal composition. That density matters. It suggests rock and metal in greater proportion than many outer moons possess. It suggests a body with enough interior complexity to matter, but not enough size, on its own, to explain the violence seen at the surface. The usual sources of internal heat seem inadequate. A world this small should have cooled far more thoroughly. If radioactive decay were the main engine, it would likely not sustain such overwhelming activity. If early formation heat were the answer, much of that energy should long ago have faded into the black outside. Yet Io glows with heat in scattered regions, erupts through great plumes, and paints itself over with fresh deposits of sulfur and silicate material. The surface does not act old. It acts injured and restless, as if some hidden force keeps reopening it. That hidden force is not truly hidden, though it takes careful thought to feel its weight. Jupiter pulls on Io with enormous power, but Jupiter does not act alone. Europa and Ganymede help hold Io in an orbital rhythm that prevents its path from becoming fully circular, because the orbit keeps a slight stretch. Jupiter's pull changes just enough during each revolution to flex the moon again and again. The body is bent, released, bent again, never allowed to settle. Rock behaves slowly under such stress, but it does behave. It warms, it strains, it yields. Over time, this tidal kneading turns orbital energy into internal heat. The explanation is elegant and severe. Io is not simply warmed from within. It is worked upon continuously by gravity. Its very motion around Jupiter becomes a source of torment. It is heated because it cannot escape the pattern that heats it. What the cameras and detectors reveal is the surface expression of that deep and repeated strain. Hundreds of volcanic centers are identified across the moon. Lava lakes, broad flows, collapse pits, and giant plume deposits mark a landscape with very few obvious impact craters. The absence of craters is almost as revealing as the presence of volcanoes. Impacts surely occur there as they do elsewhere, but their traces do not endure for long. Fresh material buries old scars, sulfur settles, lava spreads. The ground changes too often to preserve a stable archive. On many other worlds, a cratered surface is a memory map. On Io, memory is constantly overwritten. Time remains visible, but only in brief intervals between eruptions. The moon lives in a near-present tense. Its colours deepen the sense of unfamiliarity. There are ochres, yellows, black plains, red rings, orange stains, and pale frost-like coatings, not arranged with any easy earthly resemblance. Much of this colour comes from sulphur in different forms and temperatures, mixed with silicate rock and materials altered by eruption and irradiation. But naming the chemistry does not completely ease the strangeness. The surface looks as though heat and mineral vapour have become weather. Regions spread around active centres in broad halos. Dark flows cut through brighter plains. Some volcanoes are surrounded by immense ring-shaped deposits where plume material has fallen back from great height. Seen from above, these patterns have a kind of order, yet that order feels temporary, a snapshot taken in the middle of a longer disturbance. Pele becomes one of the emblematic features of this disturbance. Its plume rises high above the surface, and around it spreads a vast red and orange deposit. This is not a mountain shaped like the volcanoes familiar on Earth. It is a volcanic centre adapted to a world with weak gravity, almost no substantial atmosphere, and deep internal forcing. Material launched upward does not encounter thick air that would break and shape the column in the terrestrial way. Instead, it arcs, spreads, and settles across enormous distances. The patterns around Pele suggest a system both violent and precise. Heat pulses upward from below, volatile compounds escape, and the moon paints itself with the fallout. The result is beautiful only in the most unsettling sense. It is a beauty made of exhaust, stress, and unstable equilibrium. Then there is Loki Patera, one of Io's largest and most intriguing volcanic depressions, where observations over time suggest a process less like an explosive cone and more like a giant overturning lava lake. Its brightness changes, its thermal output shifts. At times, one portion of the crust appears to founder and sink, exposing hotter material below, while a wave of renewal moves across the lake over many months. This is not weather, not impact, not tectonics in the earthly manner, but something between all of these, a slow breathing of molten stone across a basin wide enough to challenge easy visualization. A lava sea opening, cooling, cracking, sinking, and beginning again does not merely demonstrate that Io is active, it suggests rhythms. It suggests that beneath the spectacle of individual eruptions lies a longer pulse, one that might be tracked like a season if only observation could continue long enough and closely enough. Later missions add to this image rather than calming it. Observations by Galileo, and much later by Juno during close passes, reveal more heat, more plume sources, more fracture systems, more evidence that Io's surface is a thin skin over a depth still being fed. Infrared readings show hotspots of astonishing temperature. Some are hot enough to imply ultramafic lavas, the kind associated on Earth with a much earlier planetary age. If that interpretation is correct, then Io in some places may be producing eruptions that resemble processes from Earth's deep past, rather than its present surface geology. This creates an unusual bridge between worlds. A small moon near Jupiter may display, in active form, something closer to the early thermal violence of a young rocky planet. The outer solar system, thought of as distant and mature, begins to expose conditions more primitive than those still visible on Earth. The atmosphere of Io, if it can be called an atmosphere in the ordinary sense, adds another layer of instability. It is extremely thin, composed largely of sulfur dioxide, and it changes from place to place and from day to night. In sunlight, surface frost sublimates, and the gas becomes more substantial. Though still tenuous beyond any breathable or comfortable meaning, in darkness, much of it freezes back onto the ground. Volcanic plumes add local density and chemical variety. Jupiter's magnetosphere strips and charges particles. Auroral glows appear. The moon exists inside a continual exchange between surface, eruption, sunlight, shadow, and the surrounding field of the giant planet. Nothing about it seems static. Even the air, such as it is, arrives and departs in cycles. Because Io is so extreme, it invites a certain kind of speculation, though the facts must remain in front. Life as it is known on Earth depends on liquid water, on relatively stable chemistry, and on environmental continuity within certain bounds. Io offers very little of that at the surface. It is dry in the conventional sense, radiated, volcanically unstable, and chemically harsh. By any ordinary standard, it is deeply inhospitable. Yet the existence of sulfur-metabolizing organisms near volcanic environments on Earth leaves a narrow, imaginative opening. Not a strong one, not a likely one, but a real one. If chemistry can support microbial life in dark vents and chemically difficult niches on Earth, then the study of Io still matters as an outer boundary of possibility. It need not host life to teach something about where the limits of habitable chemistry actually stand. Perhaps more importantly, it teaches that energy alone can remake a world in ways once considered improbable. There is also the larger mystery of proportion. Why should such a small world dominate the imagination so strongly once seen? Part of the answer lies in contradiction. Io is small but cannot rest, distant but not cold in the expected way, airless yet plume-filled, ancient in origin but youthful in surface, bound to Jupiter yet strangely self-announcing, so vivid in colour and activity that it seems almost to resist its own classification. It is neither a planet nor a simple moon, nor merely a volcanic object. It is a demonstration that celestial bodies can remain in states of active imbalance for immense spans of time if their orbital setting is exact enough. Stability, in this context, does not mean peace. It means a permanent mechanism for unrest. As Voyager pulls away and Io shrinks again, the moon does not become easier to place. It becomes more difficult. The solar system has already shown storms at Jupiter and hidden rings around the giant planet, but Io goes further. It reveals that even far from the sun, a world can burn with a form of internal urgency that seems almost impossible until seen. It reveals a geology driven not by simple size or sunlight, but by resonance, repetition, and stress. It reveals that the outer planets do not merely possess moons. They command systems of influence in which smaller worlds are heated, fractured, and transformed. The journey outward is no longer a movement into simpler cold. It is becoming an encounter with forms of activity that are stranger precisely because they occur where stillness had once been assumed. Beyond Io lies Saturn, luminous and ringed, appearing at first as a return to order. Yet after this burning moon, order itself begins to look like another mask. Saturn arrives with a different kind of authority. Jupiter overwhelms by mass, violence, and electrical reach. Saturn seems, at first glance, to persuade rather than overpower. Even from great distance it appears composed, almost ceremonial, encircled by rings so clean in outline that they seem less like matter than design. For centuries the planet has carried that appearance into the human imagination. It has often seemed to be the most orderly of worlds, the one whose geometry looks finished from afar, whose pale globe and thin shining bands suggest calm control rather than upheaval. When Voyager approaches, that impression does not vanish. It deepens in one sense, because the rings truly are astonishing in scale and brightness. Yet the closer look does something subtler and more unsettling. It reveals that this famous order is made not from permanence but from fragility. The rings are not solid structures, they are swarms. They are a broad and shifting disk of countless icy bodies, dust grains and broken fragments, each following its own orbit, each responding to gravity, collisions and resonance. What seems like a flawless design from a distance becomes, under inspection, a vast controlled ruin. Their dimensions are difficult to hold in the mind. The ring system extends outward across hundreds of thousands of kilometers, yet in many regions the material is astonishingly thin. The visible breadth is immense, but much of the structure would seem insubstantial if it could be touched. In some parts, the thickness is measured in tens of meters, a scale that feels almost impossible when set against the tremendous width. A structure so broad and so narrow appears less like a wall and more like an idea traced through space. Voyager shows divisions, braided textures, waves, ringlets nested inside ringlets, and gaps carved by orbital relationships. Some of these gaps exist because of small moons moving nearby, their gravity disturbing the ring particles again and again until clear boundaries emerge. Elsewhere, tiny variations in density propagate outward like ripples across a frozen pond. Except, Nothing is frozen in place. Everything moves. Everything circles. The ring system has shape because it is continually being reshaped. This is the first correction Saturn insists upon. Its order is dynamic, not still. Stability here does not mean a final arrangement. It means a long contest among collision, gravity, and motion, one that can produce patterns of astonishing precision without ever settling into permanence. Particles strike one another, exchange momentum, spread, clump, separate, and align. Small moons open gaps. Resonances sharpen edges. Dust drifts. Ice reflects sunlight with deceptive serenity. The eye sees a clean architecture. Physics describes endless negotiation. Saturn's beauty turns out to be procedural rather than static, always maintained, never truly finished. Voyager's images reveal more detail than any telescope from Earth has been able to offer, and with detail comes the recognition that the rings preserve memory in a strange and incomplete way. They're not like a solid surface that keeps ancient scars for ages. They're more like a medium in which disturbance travels visibly. A passing moonlet can create temporary structures. Gravitational forcing can maintain repeating patterns, yet collisions also erase. Material is ground down, redistributed, and altered. The rings remember through motion rather than through fixed marks. They tell their story in waves and edges, in brightness and transparency, in the spacing of particles too numerous to count. This makes them more mysterious, not less. A mountain on a moon can be mapped and compared. A ring is more elusive. It is a place where form exists without solidity, where the arrangement is the fact that matters most. The origin of the rings remains uncertain enough to keep wonder alive. They may be the remnants of a shattered moon, broken by impact or by tidal forces when it wandered too close. They may contain ancient material left from Saturn's formation, though this possibility is complicated by the ring's brightness and by signs that they may be younger than the planet itself. They may represent not one event but several, a long history of destruction, replenishment, and rearrangement. The exact answer remains difficult because every explanation opens further problems. If the rings are young, then a dramatic disruption must have happened relatively recently on the timescale of the solar system. If they are ancient, then some process must have kept them bright, icy, and structured far longer than simple models once suggested. The system does not merely display order. It also conceals its own age. Beyond the rings, Saturn itself seems gentler than Jupiter in visible light, its atmosphere marked by bands that are more subdued, its colours softer, its cloud features more restrained. Yet this gentleness is partly a matter of perspective and lighting. Voyager still finds high winds, layered clouds, polar peculiarities, and a deep atmosphere shaped by internal heat. Saturn, like Jupiter, emits more energy than it receives from the Sun. The giant world is not passive. It too continues to radiate warmth left from its formation and slow internal contraction. The difference is one of mood rather than essence. Jupiter shows turmoil in bold strokes. Saturn hides comparable depth beneath a quieter face. The same pattern begins to repeat. Distance creates impression. Nearness revises it. Its moons intensify the revision. Even before Titan claims attention as a world of its own, the Saturnian system proves to be filled with bodies that complicate simple categories. Mimas appears scarred almost beyond belief, dominated by a crater so large that the moon seems nearly broken by the impact that formed it. Tethys bears a huge chasm, Ithaca Chasma, which cuts across a great part of its circumference. Dione and Rhea carry bright icy surfaces marked by fractures, plains, and ancient bombardment. Each object preserves some piece of a longer history of freezing, cracking, and collision. These are not merely lesser companions to the ringed giant. They are witnesses to an environment where impacts, tidal forces, and internal change have all left their mark. Enceladus is especially quiet in Voyager's time, at least compared with how later missions will understand it. Yet even early images suggest that something is unusual there. Parts of its surface show relatively few craters and a brightness so high that the moon reflects sunlight with almost unsettling purity. A heavily cratered world looks old. A smooth, bright world suggests renewal. Voyager cannot yet resolve the full story, but it provides the first strong hints that Enceladus may not be as frozen and finished as distance implies. Later, Cassini will reveal towering plumes of water vapor and ice grains erupting from fractures near the South Pole, proving the presence of a subsurface sea and turning Enceladus into one of the great astrobiological targets of the solar system. In the Voyager era, that outcome still lies ahead, but the seeds are already present. Saturn's system again refuses to keep its surprises in proportion. A moon only a few hundred kilometers wide may conceal a warm ocean beneath ice, while circling in the cold outskirts of sunlight. This possibility changes the meaning of cold. It becomes harder to treat the outer solar system as a zone where energy has simply dwindled away. Saturn's moons suggest another pattern, one in which internal heat, tidal stress, and chemical isolation preserve pockets of activity long after the sun's warmth has weakened. Cracks on icy surfaces begin to look less like mere fractures and more like symptoms. Smooth plains imply resurfacing. Bright ejecta imply freshness. A chasm may record freezing, expansion, or tectonic strain. Even stillness becomes suspicious. The calmer a moon looks, the more it invites the thought that something may be sealed beneath. The rings themselves participate in this atmosphere of hidden process. Small moons move within and around them, some acting as shepherds that confine narrow ringlets, others embedded in gaps they help maintain. Their gravitational influence is delicate yet decisive, proving that even minor bodies can sculpt large-scale structure if time and repetition are available. In this sense, Saturn's ring system becomes a lesson in how weakness accumulates into power. A tiny moon does not need to dominate the rings all at once. It only needs to repeat its influence over countless orbits. The result is edge, gap, wave, and braid. Order appears, but it is born from endless insistence rather than force. There is also a faint menace in this arrangement. The rings look clean, but they are made of collision debris. Their gleam depends on sunlight striking fragments that may once have belonged to larger bodies. The moons look whole, but many of them bear evidence of catastrophic impacts or great structural stress. Gaps in the rings suggest precision, but precision here can come from repeated disturbance. Saturn does not merely display harmony, it displays harmony extracted from destruction. That is the ordered ruin at the centre of its appeal. Everything seems placed exactly where it should be, while almost everything has likely been broken, ground, cracked, or reworked to become what it now is. Voyager 1 and Voyager 2 do not move through Saturn's realm in identical ways. Trajectory choices matter, and one choice in particular begins to shape the future of the mission. A close interest in Titan, Saturn's largest moon, influences the path of Voyager 1 so strongly that the spacecraft is directed in a way that prevents it from continuing on to Uranus and Neptune. This is not a failure but a commitment. Titan is too important to ignore. It is the only moon in the solar system with a dense atmosphere thicker than Earth's, and even from a distance that atmosphere hides its surface almost completely. What lies below the haze is unknown. The moon has the size to matter, the air to complicate perception, and the chemistry to invite speculation. Saturn therefore begins to do what Jupiter has already done in a different way. It shifts the mission from simple visitation towards selection, forcing attention onto certain mysteries at the cost of others. Before that focus narrows, the planet and its system leave a broader impression. Saturn, for all its elegance, does not offer a final model of order in the solar system. It offers something more delicate and more truthful. It shows that apparent perfection can be assembled from instability, that thin structures can span enormous distances, that ice can hide fracture and perhaps warmth, and that small bodies can maintain large patterns through persistence alone. Nothing here is merely decorative. The rings are active geometry, the moons are damaged archives. The planet glows with internal heat beneath its pale clouds. The whole system seems poised, but the poise comes from motion, not rest. And at the edge of that poised complexity waits Titan, still hidden behind its orange veil, giving no clear sign of whether it is simply another moon or something much stranger. Titan does not announce itself with the violence of Io or the exposed geometry of Saturn's rings. It withdraws instead. It appears behind layers of haze, wrapped in an atmosphere so thick that the surface remains concealed from ordinary sight. This alone makes the moon feel different from almost every other object encountered so far. Most worlds in the outer solar system show their scars openly. Their craters, fractures, ridges, and plains lie under direct light, waiting for cameras to approach. Titan refuses that kind of viewing. It gives shape first and detail later. It lets the eye see a globe, a soft orange disk, a body suspended near Saturn, but it withholds the ground beneath its clouds. The effect is immediate and lasting. Secrecy becomes part of the moon's identity. That secrecy matters because Titan is not a minor satellite in any simple sense. It is larger than the planet Mercury, though less massive, which means that much of its body is made from lighter material such as water ice mixed with rock. It moves far beyond Saturn's main rings, following a nearly circular orbit around the giant planet, and at that distance sunlight is already weak. The warmth that reaches Titan from the sun is slight, so slight that ordinary water there is harder than stone. Yet despite the cold, the moon possesses a dense atmosphere, the only thick moon-wide atmosphere known in the solar system. Nitrogen dominates it, as nitrogen dominates Earth's air, but the resemblance is only partial and quickly becomes strange. Mixed into Titan's atmosphere is methane, along with other hydrocarbons and organic compounds created higher up when sunlight and energetic particles break molecules apart and allow them to recombine in more complex forms. A world of bitter cold begins to produce chemistry that seems, in outline, uncomfortably familiar. Voyager can sense some of this, but it cannot fully penetrate the haze. Its images show a soft sphere with little surface detail, and that absence becomes one of the mission's most suggestive findings. If the atmosphere is thick enough to hide the ground completely, then whatever lies below has been sheltered from direct inspection for ages. The veil itself becomes a scientific object. Layers of haze stack through the upper atmosphere. Light scatters. Colour shifts toward orange and brown because tiny particles called tholins, complex organic residues produced by chemistry in the air, suspend themselves through the atmosphere and settle slowly downward. Titan is not merely wrapped in gas. It is wrapped in a steady fall of altered matter. Its sky is manufacturing surface material. This is the second correction Titan imposes. It is not only hidden, it is chemically active, high above the unseen planes. Sunlight drives reactions that create ever more elaborate carbon-based compounds. The process does not imply life, and caution remains necessary. Chemistry is not biology. Organic molecules are not organisms. Yet the distinction, though clear, does not erase the power of the comparison. On early Earth, a thick atmosphere, active chemistry. and the presence of suitable liquids formed part of the path toward more complex structures. Titan now presents some of those ingredients in an alien combination. The temperatures are far lower. The liquid's not water at the surface, but methane and ethane. The energy available is weaker. Still, the pattern unsettles by echo. A moon so far from the sun begins to resemble a distant, distorted experiment in prebiotic possibility. The deeper picture emerges years later through the work of Cassini and the Huygens lander, but the mood belongs naturally with Voyager, because Titan's mystery begins there, in obscurity. Cassini's radar and infrared instruments finally lift part of the veil. Beneath the haze lies a world with river channels, deltas, broad dark plains, dune fields, lakes, and seas. At first this sounds almost ordinary, as though Titan has simply borrowed the language of Earth. Yet every familiar word must be altered the moment it is used. The rain is methane. The lakes are methane and ethane. The bedrock is water ice, hard as mineral. The dunes are built from dark organic grains. The cold is so intense that the entire weather cycle is based on substances that on Earth would be gases, fuels, or fleeting traces. Titan repeats the pattern of a living planet without repeating its substance. It becomes, in this sense, one of the most profound imitations in the solar system. Its surface temperature rests near 94 degrees above absolute zero, cold enough to freeze ordinary expectations along with water itself. At such temperatures, methane can exist as gas, liquid, and ice, and so Titan develops a full methane cycle with clouds, rainfall, runoff, and evaporation. Channels cut the landscape, shorelines shift. Some regions appear smoothed by flowing liquid, while others preserve wide seas in the polar zones. Kraken Mare, Ligia Mare, and other hydrocarbon seas gather in the high latitudes like dark eyes staring upward through the haze. Their surfaces can be remarkably calm, though not always. There are hints of waves under the right conditions, hints of seasonal changes, hints even of transient bright features that appear and disappear. At times these strange sea brightenings are called magic islands, though the phrase explains nothing. They may be foam, waves, suspended solids, or bubbles of nitrogen rising through the liquid. Each interpretation remains tied to real physics, yet the phenomenon continues to feel elusive because Titan's liquids are so unfamiliar that the behavior of its seas still resists ordinary intuition. On land, the moon is no less peculiar. Vast equatorial dune fields stretch for hundreds of kilometers, shaped by winds moving through dense cold air. In some places there are rounded cobbles and evidence of transport by liquid flow, seen directly by Huygens after its descent. The probe lands on a plain that appears damp, compact, and strewn with icy stones rounded by processes that resemble erosion. The scene is both alien and disarming. Nothing is green or warm or biologically busy, yet the textures recall floodplains, dry channels, and weathered gravel. Huygens records the atmosphere during descent, measuring temperature, pressure, and winds, and reveals a layered air column more structured than many had guessed. There is even a region of unusual calm in the upper atmosphere, a zone where winds above and below behave differently, as though Titan's sky contains a pause. The exact cause remains difficult to specify. Later analyses also suggest a complicated ionosphere, perhaps even more than one electrically active layer, shaped by solar radiation, Saturn's magnetospheric influence, and Titan's own chemistry. Again, the same pattern returns. The closer the study becomes, the more Titan resembles a system rather than a single object. Air, surface, liquid, organics, and hidden interior all appear to be in exchange. That hidden interior is perhaps the quietest mystery of all. Beneath the frozen crust, Evidence points to a subsurface ocean made not of liquid hydrocarbons but of water mixed with ammonia and salts, kept from freezing solid by pressure, chemistry, and residual internal heat. Gravity measurements and rotation data support this possibility. If true, Titan has two very different liquid environments, one on the surface and one buried far below it. On top lies a methane world exposed to atmosphere and seasons. Underneath lies a dark water ocean isolated beneath ice. These two domains may have little direct contact, or perhaps rare events such as impacts or cryovolcanic episodes allow material to move between them. That possibility is especially compelling because it offers a bridge between chemistry that resembles the organic haze of the atmosphere and chemistry more compatible with liquid water below. No firm proof exists that such exchange happens often or effectively. Still, the idea persists because it joins what is known into a larger question. If Titan holds organic compounds above and a water-rich ocean below, then over long spans of time the Moon may have carried ingredients that, elsewhere, are associated with the threshold of life. Care is needed here. Nothing observed on Titan confirms life. No instrument has found organisms. No surface image reveals anything that exceeds chemistry and geology. The Moon is extremely cold, and its surface liquids are chemically harsh by terrestrial standards. Methane can act as a solvent, but not in the same broad way water does on Earth. Reactions proceed differently there, often more slowly. Energy is scarce. Yet Titan continues to invite serious speculation precisely because it does not fit comfortably into dismissal. Laboratory work shows that complex organics relevant to biology can form under Titan-like conditions. The atmosphere manufactures heavy molecules and lets them drift down. Some researchers consider whether membranes unlike those on Earth could, in principle, form in methane liquid. Others regard the deep-water ocean as the more plausible site for prebiotic chemistry. Neither path has crossed the line into evidence for life, but both are anchored in observation enough to remain worth following. Titan does not promise biology. It sustains the possibility that chemistry alone can become unexpectedly rich in a place where instinct once predicted sterility. Its seasons deepen the impression of a living system without granting the word life. Titan's year is bound to Saturn's long orbit around the Sun, so each season lasts many Earth years. Clouds gather and thin. Rains may shift between hemispheres over long intervals. Lakes change in extent. Surface brightness alters subtly in response to weather and deposition. Even the haze itself varies. Nothing happens quickly by human standards, yet over time Titan reveals movement everywhere. The atmosphere is not frozen in place, the seas are not fixed, the dunes are not eternal. A moon that first seems hidden and still turns out to be operating on a patient cycle of change. This patience helps explain why Titan draws future missions toward it. Dragonfly, a rotorcraft mission developed by NASA, is planned to explore the Moon by flying through its thick air and visiting multiple locations. That concept would seem fantastical on most worlds, but Titan's dense atmosphere and low gravity make it practical. A machine can rise from one plane, cross dark dunes or icy ridges, and settle elsewhere to sample chemistry and geology. The mission is designed not because Titan is easy, but because it is layered. It offers atmosphere, surface liquids, organics, impact sites, and possible contact zones between different chemical worlds. Every one of those environments holds clues not only about Titan itself, but about the broader question of how chemistry behaves when given time, carbon, and changing conditions. What makes Titan so haunting is that it does not shout any of this. It remains muted in colour, quiet in tone, and slow in change. It does not burn like Io. It does not glitter like Saturn's rings. It does something more difficult to forget. It rearranges the idea of familiarity. Rivers are there, but not of water. Rain falls, but not from water clouds. Pebbles lie on the ground, yet the ground itself is water ice. Organic chemistry fills the air, but no leaf, cell, or shell appears. It is as though nature has repeated part of a known design while withholding the expected outcome. That gap between pattern and conclusion is where Titan's mystery resides. It is a world that looks almost ready to mean something recognizable, and then remains just beyond recognition. The haze does not only cover the surface, it covers interpretation. Beneath it lies a moon whose weather, chemistry, and hidden ocean keep suggesting that the boundary between the familiar and the alien may be thinner than once believed, even in the deep cold beyond Saturn. Beyond Saturn, the solar system changes its mood again. The great ringed planet, with its pale light and elaborate order, gives way to distances that feel less adorned and more remote. Here the sun weakens further, and its power begins to look less like command and more like a memory that still reaches outward. The space between worlds widens. Light takes longer to travel. Signals grow fainter. The known planets ahead have never been seen at close range by any human-made instrument before Voyager. Uranus and Neptune have existed in telescopes as cool disks, dim and disciplined, moving with mathematical certainty through the dark. Yet certainty of orbit says little about character. As with Jupiter and Saturn, the farther the probe travels, the less trustworthy the old impression becomes. The next worlds are colder, quieter in appearance, and strangely more difficult to understand. They do not erupt into spectacle at first sight. They deepen mystery by withholding scale, by behaving in ways that seem too severe or too subtle for worlds so distant from the sun. Uranus comes first, and its first great strangeness is visible even before finer details emerge. The planet is tipped. Its axis lies so far over that Uranus appears almost to roll along its orbit. Instead of spinning like a top with a modest lean, it turns like a barrel, presenting one pole and then the other toward the sun over the long course of its year. This is not a small irregularity. It is one of the most dramatic tilts of any major planet, and it changes the meaning of season entirely. Each pole spends long stretches in sunlight, followed by long stretches in darkness. The ring system and the moons align accordingly, circling a planet that seems to have suffered some ancient catastrophe, or else to have formed under conditions no longer easy to recover. One leading idea holds that Uranus endures the aftermath of a colossal impact early in solar system history, an oblique blow large enough to tip the entire world without destroying it. Another possibility is more complex and slower, involving multiple collisions or long-term gravitational interactions. The facts remain incomplete. What is clear is the outcome. Uranus does not merely lean, it inhabits a posture of lasting imbalance. When Voyager approaches, the planet first seems almost disappointingly plain, a smooth blue-green globe with little of Jupiter's pattern or Saturn's soft banding. Methane in the upper atmosphere absorbs red light and leaves the disk washed in cyan and turquoise. In visible light it appears calm, nearly featureless, as if cold has erased weather itself. Yet this calm is partly an artifact of viewing conditions and limited contrast. Later telescopes and improved analysis reveal clouds, storms, and seasonal changes. But even in Voyager's time, Uranus is already stranger than plainness allows. It emits surprisingly little excess heat compared with the other giant planets. Jupiter and Saturn radiate substantial internal warmth. Neptune does as well. Despite being even farther from the sun, Uranus, by contrast, appears almost subdued from within. It gives off little more energy than it receives. That fact is deeply puzzling. If Uranus formed like the other giant planets, and if internal heat should linger within such a body, then why does so little of that energy emerge now? Perhaps the ancient event that tipped it also disrupted its interior and trapped heat in an unusual way. Perhaps layers inside the planet prevent efficient transport upward. Perhaps the world is not less active in total, but differently structured, with deep gradients and chemistry that suppress outward flow. The measurements invite explanation, but no explanation is fully satisfying. A planet so violently tilted should not also seem so inwardly quiet. Yet it does. Its magnetic field intensifies the puzzle. Voyager shows that Uranus possesses a magnetic field tilted steeply relative to its rotation axis and offset from the planet's center by a large amount. The result is an invisible structure that appears lopsided and unstable in geometric terms, as though the source of the field lies in a shell or region not symmetrically arranged within the planet. Earth's magnetic field, for all its complexity, is often imagined as centered and roughly aligned. Uranus refuses that simplification. Its magnetosphere must wobble and twist dramatically as the planet rotates, presenting a changing face to the solar wind. Space around Uranus therefore becomes a moving maze of charged particles and magnetic lines, shaped by a geometry that seems almost improvised. Again the pattern returns. The planet first appears simple and then, under closer study, becomes harder to picture in stable form. The rings of Uranus are another correction. Before their discovery from Earth in the late 20th century, the planet seemed to lack such adornment. Yet Voyager confirms a system of narrow, dark rings, much less bright and broad than Saturn's, but no less revealing. These rings are shadowy and austere, made from darker material that reflects far less light. Their existence suggests shepherding moons, collisions, and persistent dynamical shaping. If Saturn's rings look like luminous architecture, Uranus offers a harsher version, one less generous with beauty and perhaps more revealing of the underlying damage from which rings can grow. The outer solar system continues to repeat a lesson in variation. Similar structures exist around different worlds, but each system expresses them in a different mood. Its moons extend that lesson. Miranda is the most startling. Small, irregular, and difficult to explain, it bears on its surface enormous cliffs, patchwork terrain, and structures that seem assembled from pieces that do not belong together. Some regions look heavily cratered and ancient. Others appear younger, ridged, and resurfaced, as though parts of the moon have been torn apart and reformed or upwelled from within after old damage. One interpretation imagines that Miranda was shattered by a colossal impact and then reassembled under its own weak gravity. Though proving such a history is difficult, another favours intense internal deformation, driven by tidal stresses during a past orbital resonance. Whatever the exact mechanism, the surface looks unfinished in a way that unsettles the eye. It resembles neither total ruin nor coherent renewal, but something between, a small world partly rebuilt and never completely smoothed over. Ariel, Umbriel, Titania, and Oberon offer other combinations of fracture, crater, and icy plain, together suggesting that Uranus's moons have not simply drifted unchanged through deep cold, they have cracked, shifted, and preserved signs of forces no longer easy to trace. Then Voyager moves outward to Neptune, and the quiet turns sharp again. Neptune is farther from the Sun than Uranus, receiving even less warmth, yet it proves more active in visible ways. This alone is astonishing. The planet shines deep blue because methane absorbs red light, but the colour is more saturated, and the atmosphere reveals high clouds and strong contrast. Winds tear across the planet at extraordinary speeds, among the fastest known in the solar system. Dark storm systems appear and later vanish over the years, including the feature Voyager makes famous, the Great Dark Spot. It resembles Jupiter's Great Storm only in the broadest visual sense. It is not red, not necessarily long-lived on the same scale, and perhaps not as stable. Rather, it seems to be one expression of an atmosphere that remains dynamically violent despite the weak sunlight available so far from the Sun. Neptune radiates more internal heat than Uranus, and somehow that internal energy translates into a meteorology of startling power. Here again, the solar system refuses a simple gradient from inner activity to outer stillness. Distance does not make Neptune quiet. It makes the source of its unrest harder to account for. Its internal structure, like that of Uranus, is thought to include a deep mantle of water, ammonia, and methane in exotic states under tremendous pressure, above a rocky core and beneath a hydrogen-helium envelope. The old term ice giant describes composition more than appearance, because these materials do not exist as familiar ice in most of the interior. They enter compressed, hot, electrically active forms that challenge ordinary intuition. In such depths, water may be part of a dense fluid ocean unlike any sea imagined on Earth. Carbon under enormous pressure may separate and sink, perhaps even forming structures or processes that sound almost poetic when translated into plain language. Some scientists have speculated about diamond rain in the interiors of ice giants, not as fantasy, but as a consequence of chemistry under extreme conditions. Whether such processes occur exactly as imagined remains uncertain, but the possibility belongs naturally to these worlds. They are not cold simply because their upper clouds are frigid. Deep below, pressure and heat may create regimes more akin to furnaces than to frozen wastelands. Neptune's magnetic field mirrors Uranus in one crucial way. It too is strongly tilted and offset, implying that the mechanism generating the field sits in an unusual shell rather than in a neat central dynamo. Once might be an anomaly. Twice suggests a class of worlds whose interiors operate according to patterns not fully represented by Earth, Jupiter, or Saturn. If Uranus and Neptune are both asymmetric in magnetism, then something about the ice giant category itself may encourage dissented order. The field becomes another sign that these planets are not failed versions of the larger giants, but worlds of a distinct kind, with their own internal logic still only partly known. Then there is Triton, Neptune's great moon, perhaps the most haunting body encountered in this outer stretch. It orbits backward, opposite the planet's rotation, which strongly implies that it didn't form alongside Neptune in the usual way. It was almost certainly captured, a large body taken from elsewhere, likely from the region now called the Kuiper Belt. That capture would have been a violent rearrangement, disturbing any earlier regular satellite system and reshaping the architecture around Neptune. Triton bears the marks of this difficult history. Its surface is young in many places, with relatively few impact craters. It shows strange terrain, cantaloupe-like textures, smooth plains, and dark streaks laid down by geyser-like plumes that Voyager detects rising from the surface. Nitrogen appears to erupt or sublimate from below, driven by a weak seasonal sunlight or deeper processes not yet fully resolved. A moon near the edge of the classical planetary system is found venting material into a thin atmosphere, renewing parts of itself and preserving evidence of a captured past. The outer frontier is not ending in silence, it is ending in complications. Triton also raises one of the quietest and most enduring speculative possibilities of the Voyager journey. If it is captured Kuiper Belt material, and if its interior has been heated by tidal evolution after capture, then perhaps beneath its frozen crust there has once been, or may still be, a hidden ocean. The evidence is indirect and incomplete, drawn from geology, density, surface youth, and models of internal heating. Yet the possibility matters because it extends the pattern already seen elsewhere. Europa, perhaps. Enceladus, almost certainly. Titan, likely. Now Triton, maybe. Oceans begin to appear not as rare oddities but as recurring hidden features of the outer solar system, concealed under ice, separated from sunlight, maintained by sources of heat that have little to do with daylight at all. The farther outward the probe travels, the more it discovers places where the most important liquid may be the one no camera can see. By the time Voyager leaves Neptune behind, the planetary tour has transformed from a sequence of destinations into a revision of cosmic expectations. Uranus introduces a world tipped nearly on its side, magnetically off-center, ringed in darkness, and surrounded by moons that look broken and partly rebuilt. Neptune responds with deep blue storms, impossible winds, asymmetric fields, and a captured moon that still exhales into the cold. Neither world offers the bright immediacy of Saturn's rings or the violent revelation of Io, yet each leaves a more durable unease. They suggest that remoteness does not simplify nature. It strips away the comforting assumptions carried outward from the inner planets and replaces them with systems whose rules are only partly visible. These ice giants do not conclude the old map of the solar system. They open it. Beyond Neptune, the planets are nearly finished, but the mystery is not. The sun's empire thins ahead, and the spacecraft now begin to move toward a boundary that cannot be seen in any camera image at all. After Neptune, the journey changes more completely than it does at any earlier stage. Up to this point, the Voyagers move from one grand encounter to another. Jupiter fills the frame with storms and burning moons. Saturn surrounds itself with rings and hidden seas. Uranus and Neptune deepen the strangeness with tipped axes, dark winds, and captured worlds. Each new target offers a visible center, a place where the eye can rest and where the instruments can gather around a planet as though around a fire in the cold. Once the last giant planet falls behind, that pattern ends. There are no more scheduled close passes. No larger disk waits ahead to swell in the camera view. No moon system lies ready to resolve from bright points into mountains, fractures, or plumes. The probes keep moving, and in one sense they move faster than before, because the giant planets have flung them outward with tremendous efficiency. Yet the faster they go, the quieter the journey becomes. Distance is no longer just the medium between events. Distance becomes the event itself. This is not emptiness in the absolute sense. The space beyond the major planets still contains bodies, dust, scattered ice, magnetic structure, and the long outward breath of the sun. Yet it feels different because the objects are farther apart and because the scales of observation begin to separate from human instinct. A moon can be photographed and named in a single frame. A boundary in particle density or magnetic pressure must be inferred from instruments and patience. The drama grows less visible and more abstract, though no less profound. The Voyagers now leave behind the old theatre of bright planetary encounters and enter a region where the most important changes happen in graphs, counting rates, and faint shifts in the character of the plasma around them. Voyager 1 and Voyager 2 are no longer twins in trajectory, though they remain siblings in purpose. Voyager 1, after Saturn and its decisive pass by Titan, is bent onto a path that carries it above the plane in which most of the planets orbit. Voyager 2, having continued on to Uranus and Neptune, departs on a different angle, heading below that plane. The two spacecraft begin to separate not only from Earth, but from one another, like messengers sent through different exits of the same vast chamber. This divergence is scientifically useful. It allows the outer reaches of the solar system to be sampled in more than one direction. It also carries a quiet symbolic weight. The mission, once so strongly tied to a single grand tour, opens outward into multiple unknowns. There is no final common road. The future is forked. As the planets recede, the sun itself begins to change character. From Earth, it dominates all ordinary experience of the sky. Even from Jupiter, it remains the clear master of the system, bright enough to define day, shadow, and energy. Beyond Neptune, it is still the central star, still far brighter than any other point in the sky. Yet it has begun to lose something of its apparent absolute rule. It becomes smaller, harder, more concentrated, a brilliant object rather than an enveloping presence. The warmth it supplies is faint. Solar panels would be nearly useless here. Illumination is thin. The surrounding darkness starts to resemble interstellar darkness, not because the sun is absent, but because it is no longer sufficient to fill the scene. The probes continue under the power of their radioisotope generators, carrying a private source of heat and electricity, as though each one has brought its own ember from home. This ember begins, slowly and irrevocably, to fade. The radioactive fuel decays according to its own timetable, and each year a little less electrical power is available. The process is expected from the beginning. There is no single failure, no dramatic extinguishing. Instead, there is a long negotiation between need and supply. Engineers on Earth must decide which systems can remain active, and which must be turned off to preserve the most valuable measurements for the longest possible time. Heaters, instruments, backup units, and at times even familiar capabilities become expendable. The spacecraft do not age in the way living bodies do, but they do grow more selective. They shed function in order to continue. Each surviving instrument becomes more precious because it remains part of a narrowing conversation between Earth and an ever more distant machine. Communication itself changes meaning in this phase. During the planetary encounters, delays are noticeable but still emotionally manageable. Commands are sent, data returns, and the rhythm of response, though stretched, still belongs to human planning. As the Voyagers move farther outward, the delay lengthens into something more severe. A signal must travel for many hours before it reaches the spacecraft, and the reply must spend many more hours crossing back. Conversation becomes impossible in any ordinary sense. Real-time intervention vanishes. Every instruction is a commitment sent into the dark long before its consequences can be known. Every engineering adjustment becomes an act of trust. The giant antennas of the deep space network listen for power levels so faint that they border on absurdity, tracing whispers from distances measured not in the old way of flight paths and launch windows, but in astronomical units layered one beyond another. This is the stage of the journey in which Voyager becomes less a vehicle of arrival and more a test of endurance. The cameras, so central to public imagination during the planetary flybys, gradually lose practical priority. There is little point in imaging darkness or objects too distant and dim to yield detail. The mission turns toward fields and particles, toward the surrounding medium itself. The probes become weather stations in a place where weather is magnetic, energetic, and nearly invisible. They sense solar wind slowing and shifting. They register changes in charged particles. They map, in narrow and patient fashion, the outer influence of the sun. Their work becomes quieter to describe, but perhaps grander in implication. The spectacle of worlds gives way to the study of a border, before that border fully arrives. However, there is a moment of looking back. In the year 1990, long after Jupiter and Saturn have fallen behind Voyager 1, the spacecraft turns its camera toward the inner solar system one last time. The resulting images are not technically superior to the close-up portraits of the giant planets. In one sense, they are almost disappointing. The worlds appear as tiny points or delicate streaks in scattered sunlight. Yet among these images is Earth, seen from an immense distance as a faint mote suspended in a sunbeam. The photograph becomes one of the defining images of the space age because it shrinks the familiar beyond comfort. Continents, weather, wars, cities, languages, ambitions, all are too small to resolve. The planet that launched the spacecraft is reduced to a nearly invisible grain of light. There is no accusation in the image, no philosophy imposed by the machine. There is only scale, and scale is enough. Afterward, the cameras are turned off for good. The outward gaze continues, but the visual chapter is largely finished. What remains is more austere and, in some ways, more intimate. The spacecraft's spin or hold orientation with exquisite discipline. Tiny thrusters correct motion. Gyroscopes and star trackers keep their sense of direction. Electronics designed in the early 1970s continue to operate in a region for which they were built with faith rather than precedent. The farther they travel, the less likely rescue, replacement, or even close comparison becomes. New missions may follow similar distances one day, but each Voyager remains solitary in its exact history. Every error survived, every anomaly corrected, every component still functioning beyond expectation adds to the quiet improbability of the mission. The region they move through is often spoken of as the outer solar system, yet this phrase hides how gradual the transition really is. There is no wall marking the end of the planetary realm. Instead, there is a thinning of obvious structure. Neptune's orbit is crossed. The broad zone once associated with Pluto and the icy bodies beyond the giant planets becomes conceptually nearer, even if not directly visited by Voyager. Countless small worlds may exist out there, remnants of formation and collision, preserved in deep cold. Some follow stable paths, others are perturbed into more elongated or scattered trajectories. The probes do not weave among them like ships through islands. Space remains too large and the objects too sparse for that image to hold. Yet the idea matters. The giant planets are not the true edge of the solar system. They're only the last large worlds before the system begins to dissolve into belts, disks, clouds, and populations of bodies too small or too dark to dominate the scene. There is a subtle tension in this phase between motion and stillness. The spacecraft are moving faster than any previous human-made objects moving away from the sun. Yet the view ahead appears almost unchanged. Stars do not rush past. Constellations do not visibly distort. The nearest stellar destinations remain unimaginably far away even now. The probes can cross the realm of planets within decades, but the gulf to another star remains a task for thousands or tens of thousands of years. This mismatch between speed and insignificance deepens the mystery of scale. Human engineering has learned to leave the planets behind. It has not learned, even remotely, how to make interstellar distance feel small. The Voyagers therefore occupy a special interval. They are no longer planetary probes in the ordinary sense, yet they are not truly interstellar craft in the full experiential sense either. They are crossing the long threshold between these states. That threshold does something to time. On Earth, decades pass and mission teams change. Engineers retire, scientists age. The world that launched Voyager alters politically, technologically, culturally, and linguistically. While the spacecraft continue with the same patient objective logic written into them from the start, the probes become moving relics of an earlier era that somehow remain functionally present. Their computers are ancient by modern standards. Their memory is small. Their architecture belongs to a different age of electronics. Yet in the outer dark, old design proves not weakness but resilience. Simplicity, redundancy, and discipline have carried them farther than many more sophisticated systems might endure. This too contributes to the strange emotional character of the long exit. The farther the spacecraft travel, the more they seem less like machines of a single decade and more like durable thoughts set loose in the solar system. The darkness around them does not become empty enough to lose meaning. It becomes sparse enough that every measurement matters more. cosmic rays, solar particles, magnetic direction, plasma waves. All of these begin to trace a story about the sun's dominion and where it weakens. The planetary tour is over, but the deeper question grows stronger. How far does the star's influence extend? What shape does that influence take as it moves against the surrounding galaxy? Is the solar system enclosed within a neat bubble, or something more asymmetrical and disturbed? The answers cannot be photographed directly. They must be approached through numbers accumulated over years of quiet travel. The great visible drama has ended. In its place comes a more difficult form of wonder, one based on persistence, abstraction, and the realization that the frontier ahead may not look like a frontier at all until the instruments insist that it is there. By now, the long exit has become its own kind of encounter. The spacecraft move on without any planet left to greet them, and yet the journey feels no less charged. A machine launched from Earth continues into a region where sunlight weakens, power dwindles, communication slows, and the familiar architecture of the solar system gives way to something larger and less certain. The emptiness begins to show structure. The silence begins to carry pressure. Ahead lies the invisible frontier where the solar wind meets the wider galaxy, and where the sun's authority, stretched across immense distance, begins at last to falter. The boundary ahead cannot be seen in any ordinary sense. No camera frame can hold it. No disk grows brighter as the spacecraft approaches. There is no horizon line, no coloured band in the dark, no visible frontier laid out across space. Yet the sun has been shaping its surroundings all along, pushing outward through the solar system in a ceaseless stream of charged particles called the solar wind. That wind carries the sun's magnetic field with it, stretches it, twists it, and presses outward against the thin gas and particles that drift between the stars. For a long time, this outward pressure dominates. It creates a vast cavity around the solar system, a region where the solar wind remains the main local force. This region is called the heliosphere. It is often imagined as a bubble, though the truth is less tidy. A bubble suggests smooth symmetry, a neat inflated shell around the sun. The actual structure is likely more distorted, compressed in some directions, extended in others, and always responding to changes in the surrounding interstellar medium and to the changing activity of the sun itself. Even before the Voyagers reach its edge, the very shape of this great domain is uncertain. This uncertainty matters because the heliosphere is not only a structure, it is also a form of protection. The solar wind and the magnetic field it carries help reduce the flux of some galactic cosmic rays entering the inner solar system. They do not stop them entirely, but they modulate them, deflecting and slowing part of the bombardment that drifts through the galaxy from distant energetic events such as supernova remnants and other violent accelerators of particles. Earth exists well inside this vast magnetic outflow. So do all the planets. The heliosphere therefore acts less like a wall and more like a moving influence, a shield with openings, fluctuations, and weak points, yet still a shield. To reach its edge is not merely to cross a distance, it is to approach the place where the sun's authority over nearby space begins to fail. The first major sign of that failure is the termination shock. So long as the solar wind streams outward faster than the speed at which pressure disturbances can move through it, it remains effectively supersonic, but farther out, after losing energy and pushing against the surrounding medium for billions of kilometers, it slows. At some point it must drop below that supersonic state. The region where this happens is not a wall in the ordinary sense, but a broad and active transition. Voyager encounters it not through sight, but through altered readings in plasma, magnetic fields, and energetic particles. The solar wind is shocked, slowed, heated, and made more turbulent, Beyond that lies the heliosheath, a zone where the sun's outflow still moves outward overall but no longer with its former confidence. It is compressed, agitated, and beginning to mix in influence with the matter outside. If the inner solar system can be imagined as lying within the easy reach of a star, then the heliosheath is the region where that reach trembles. Voyager 1 reaches the termination shock first. The crossing is not clean in the human sense. It is not like passing a line painted on a floor. Data suggest a transition that may involve repeated encounters, irregular structures, and local fluctuations. Voyager 2, travelling through a different region of the heliosphere, encounters its own version of the same boundary at a different distance. This difference is important. It implies that the heliosphere is asymmetric. The sun's bubble is not centered and uniform like a textbook diagram. It is shaped by outside pressure, by the local interstellar magnetic field, and perhaps by time-varying conditions carried outward from the sun over the course of the solar cycle. One side begins to falter sooner than another. Even the shield of a star turns out to be uneven. Inside the heliosheath, the journey becomes stranger still. This is not interstellar space yet, but neither is it the orderly solar wind of the inner regions. Charged particles behave differently. Magnetic fluctuations become more significant. The solar outflow slows further and seems, in some measurements, to lose much of its straightforward radial motion. It is as though the wind that once rushed from the sun in dominance now finds itself crowded, turned, and compressed near its own limit. The region is not empty confusion. However, it has structure, it has gradients, it has pressure. The Voyagers detect changes in anomalous cosmic rays, particles thought to originate as neutral atoms from interstellar space that become ionized, are picked up by the solar wind and later accelerated at the outskirts of the heliosphere. These particles rise and fall in ways that help map the changing character of the region. The farther outward the probes travel, the more the language of the mission becomes one of inference. Boundary, sheath, pressure, turbulence, modulation, flux. Each term is exact enough for science and still strangely inadequate for imagination. What makes the heliosheath so compelling is that it is both edge and interior. It belongs to the heliosphere, yet it is already shaped by what lies beyond. It is a frontier in the purest sense, where two environments meet, and neither yields entirely at once. One can imagine it as surf, except the analogy is imperfect. There is no water, no shore, no foam visible to the eye. There are only particles and fields. Yet there is still a contest, still a slowing, still a compression where one great medium encounters another. The sun's outflow, which has streamed outward since long before Earth existed in its present form, begins here to lose the clear open space it once occupied. The galaxy pushes back. The heliopause is the deeper threshold beyond this region, the outer boundary of the heliosphere itself. It marks the place where the outward pressure of the solar wind is balanced by the inward pressure of the interstellar medium. Again, balance does not mean symmetry or stillness. It means contest held in dynamic form. For years before the crossings, scientists debate what the transition might look like. Some expect a sharp boundary. Others imagine a more tangled mixing layer. Some wonder whether the magnetic field direction will change dramatically at the crossing. Others suspect that local complexities will obscure any simple signature. The Voyagers approach with only their instruments to decide the matter, and even then the answer arrives through ambiguity before clarity. Voyager 1 provides one of the most extraordinary examples of how a spacecraft can discover something important, almost by accident, or rather by persistence in the absence of a hoped-for instrument. Its direct plasma instrument is no longer functioning during the crucial approach to the heliopause. This might have seemed like a crippling loss, yet the spacecraft still carries a plasma wave instrument, and nature supplies an event that allows measurement by indirect means. A disturbance caused by solar activity travels outward and eventually reaches the region around Voyager. The plasma there begins to oscillate, and from the frequency of those oscillations, scientists infer the density of the surrounding medium. The result is striking. The density is much higher than expected for the solar wind within the heliosphere, and consistent instead with interstellar plasma. In other words, without directly measuring the flow in the old way, Voyager 1 appears to be sitting in a new environment. At nearly the same time, energetic particles associated with the heliosphere drop sharply, while galactic cosmic rays increase. The shield has thinned enough, or the spacecraft has passed beyond it enough, that the broader galaxy is beginning to announce itself. The sun's protective modulation is still present in a subtle sense, but it is no longer the dominant local condition. Voyager 1 has crossed into interstellar space, yet even here simplicity fails. The magnetic field direction does not swing as dramatically as some models once led many to expect. Instead, it remains surprisingly similar across the transition, at least in broad orientation. This creates debate. Has the spacecraft really crossed the heliopause, or is it in some transitional magnetic layer still attached to the heliosphere in a less obvious way? Over time, the balance of evidence favours the crossing interpretation, especially because of the plasma density and the persistent particle changes. Still, the episode leaves a valuable impression. Even at the edge of the sun's domain, nature declines to produce a perfectly theatrical signal. The crossing is real, but it is embedded in complexity. The galaxy does not wait on the other side with a signpost. Voyager 2 later offers an even richer version of the crossing, because more of its plasma instrumentation remains operational. Its measurements confirm that the solar wind speed falls dramatically near the boundary, and that the plasma density beyond rises into the interstellar range. The details differ from Voyager 1's experience, reinforcing the sense that the heliosphere's outer limit is asymmetric and responsive to local conditions. Two spacecraft leave the solar system's protective envelope by different routes, and do not find identical exits. This is one of the most revealing outcomes of the whole long mission. The boundary of the sun's influence is not only invisible, it is regionally distinct. It bends, it compresses, it perhaps ripples over time. The sun moves through the local interstellar medium, and the heliosphere may be shaped somewhat like the bow region around a ship, though even that image is contested. Earlier expectations of a strong bow shock ahead of the heliosphere have softened into more nuanced possibilities, perhaps closer to a gentler bow wave or a more subtle disturbance, depending on the exact properties of the interstellar medium. The frontier resists clean metaphor because it belongs to plasma physics rather than ordinary surfaces. Once beyond the heliopause, the Voyagers do not leave the sun behind in any complete sense. They continue to feel some effects of solar activity, especially when major disturbances launched from the sun long earlier arrive after their immense travel time. The spacecraft also remain gravitationally within the solar system by any practical long-term definition. The Oort cloud, if it exists in the form generally imagined, extends vastly farther out. Interstellar space in the local physical sense has begun, but the deeper outskirts of the sun's long gravitational dominion still lie ahead for many thousands of years. This distinction matters because it prevents the crossing from being mistaken for an absolute ending. The heliopause is a powerful threshold, but not the last one. It is the place where the sun ceases to dominate the surrounding plasma environment, not the place where every bond to the solar system is cut. Still, the emotional significance of the crossing is hard to overstate. For the first time, human-made objects begin to sample the matter between the stars directly. They move through plasma that did not originate from the sun. They detect cosmic rays with less solar filtering. They help define the size and shape of the Sun's protective domain by leaving it. This is not interstellar travel in the dramatic sense imagined by fiction. No nearby star grows brighter because of it. No alien world comes within reach, yet it is interstellar travel in the strictest and most patient sense. Two machines built on Earth have entered the medium that lies between stellar systems and continue to report from within it. The boundary, once approached as a scientific problem, becomes something larger through this persistence. It shows that a star is not merely a source of light and gravity. It is also an engine that carves out territory in the galaxy, a territory with edges, distortions, and weather of its own. It shows that the solar system is not suspended in emptiness, but immersed in a broader galactic environment, one with pressure, magnetic direction, and drifting particles that matter. And it shows that the deeper the mission goes, the more the old distinctions between object and environment begin to blur. At Jupiter and Saturn, the spacecraft encounter worlds. At the heliopause, they encounter context. The invisible frontier has no face, no colour, and no mountain range to name. Yet it may be the most profound landscape of the entire voyage, because it marks the place where home ceases to be the medium itself and becomes, at last, only the distant source of a fading wind. Beyond the heliopause, the voyages do not become less meaningful because they are farther away. They become harder to interpret because distance alters the purpose of a signal. In the earlier years of the mission, every transmission points back toward a nearby goal. A camera image of Jupiter returns because Jupiter is there to be seen. A magnetometer reading near Saturn matters because Saturn is shaping the field. Even the long delays remain attached to immediate physical settings. A world fills the instruments, and the signal carries part of that encounter home. In the interstellar medium, the pattern becomes more austere. The spacecraft keeps sending data, but the data now speaks of a place that has few visible landmarks. There is plasma, magnetic direction, particle intensity, subtle change in cosmic ray flux, the distant signatures of solar disturbances arriving after long travel. There is still discovery, but it comes through persistence rather than spectacle. The signal no longer says, "Here is a planet." It says, "Here is the medium between worlds." It says, "The sun's influence still reaches this far in some forms and not in others." It says, "The galaxy has texture." And beneath all of this, it says something quieter. The machine is still alive. That simple fact grows stranger with time. The Voyagers are artifacts of another technological age. Their computing power is slight by ordinary modern standards. Their memory is narrow. Their materials, design logic, and fault tolerances belong to a period when deep space demanded rugged simplicity rather than delicate abundance. Yet these old spacecraft continue outward decade after decade, not because they are sophisticated in the contemporary sense, but because they are disciplined, redundant where it matters, and astonishingly well tended from afar. A mission does not survive this long by launch alone. It survives because teams on Earth keep learning how to speak to aging hardware across impossible distances, how to interpret unusual behavior, how to conserve energy, and how to adapt expectations to what remains possible. The relationship becomes less like operation in the everyday engineering sense and more like long stewardship. Each contact with the spacecraft is part command, part diagnosis, part listening for a voice that has become almost too faint to distinguish from the surrounding silence. Power is the central limit now. The radioisotope generators continue to produce electricity as heat from radioactive decay is converted by thermocouples, but the output diminishes slowly and irreversibly. There is no repair for this, no refueling, no reversal. Each year, a little less energy is available. A deep space mission can survive many kinds of uncertainty, but not a shrinking energy budget without sacrifice. Instruments are turned off one by one. Heaters are reduced or eliminated. Systems once considered basic become optional, then impossible. Engineers decide what scientific return is worth the cost in watts. What can be endured in colder conditions than once thought safe? What component can be allowed to drift farther from its ideal temperature if it means another instrument may continue operating? In this way, the mission becomes increasingly selective. It does not simply continue, it continues by subtraction. This process gives the spacecraft an almost biological appearance, though only in metaphor. They are not living, yet they preserve function by shedding function. They enter a late stage in which the preservation of one vital capacity depends on the abandonment of another. Some instruments have already served their purpose and fallen silent. Others remain because they are uniquely suited to the environment now being traversed. A detector still counting charged particles in interstellar space is not merely one instrument among many. It is one of the few remaining ways in which a remote machine can still tell Earth something no other source can provide directly. A plasma wave instrument still hearing oscillations in the medium is not just surviving. It is preserving the mission's ability to define the surrounding density and the passage of disturbances through interstellar plasma. Each remaining sensor therefore becomes more than a device. It becomes the last representative of an entire kind of knowing. The signals themselves are extraordinary in their weakness. By the time they reach Earth, they are fainter than the background noise that surrounds the listening antennas. Recovery is possible only because the deep space network uses immense dishes, patient integration of signal over time, and increasingly refined processing. The Earth must become an instrument of listening on a planetary scale just to hear the whisper of a single machine built generations earlier. There is something almost paradoxical in this. Human communication on Earth grows faster, denser, louder, and more immediate across the decades, while one of humanity's oldest still functioning emissaries speaks more slowly and more softly than ever before. The missions exist at the far edge of intelligibility, where hearing depends on technical devotion and on the refusal to treat faintness as disappearance. Because the journey now unfolds on such vast scales, even solar events begin to acquire a ghostly quality. A burst of activity from the Sun may race outward through the solar system, crossing planetary orbits long after it has ceased to matter for daily weather on Earth, and then many months later, or even longer still, its consequences can be detected by a Voyager in the interstellar medium. A star speaking to its own farthest machines in delayed pulses is not a phenomenon easily absorbed into ordinary temporal intuition. The cause belongs to one season on Earth. The effect arrives near the spacecraft in another year entirely. In this way, the Sun remains part of the narrative long after the probes have left the heliosphere. Its disturbances continue to overtake them, weakened and stretched yet still legible. The relationship between origin and emissary is not ended. It is only extended to a timescale that makes immediacy impossible. The golden records mounted on the sides of the spacecraft acquire a different weight in this stage of the journey. They are not instruments, not transmitters, not things meant for current use. They sit attached to the probes as they have since launch, carrying encoded sounds and images of Earth together with diagrams, meant to indicate the record's origin and method of playback. Their intended audience has always been hypothetical. The records are designed for an encounter almost too improbable to take seriously and too suggestive to dismiss entirely. They may never be found. They may pass through the galaxy for millions of years in complete obscurity. The odds of interception by another intelligence are so small that practical expectation becomes meaningless. Yet the records remain one of the most compelling parts of the mission precisely because they exist in that interval between intention and impossibility. They are a message prepared for a recipient no one can name, on a timescale no institution can meaningfully manage. This makes the Voyagers peculiar among spacecraft. Most missions are deeply local in their purpose. They observe, report, and eventually stop. The Voyagers do that as well, but they also continue as objects after they stop being missions in the active engineering sense. Once their instruments fail and their transmitters can no longer be powered, they will not vanish. They will simply cease to communicate. Their physical bodies will continue on hyperbolic paths away from the sun, becoming silent artifacts with trajectories still defined but functionally beyond contact. At that point, their status changes from probe to relic. They will no longer return knowledge, yet they will continue to embody a decision made on Earth in the 1970s. A decision not only to explore the outer planets, but to send durable objects outward beyond any reasonable hope of return. The future paths of the two spacecraft deepen this impression. Over thousands and tens of thousands of years, they will drift through the sparse stellar neighborhood of the Sun, not toward any star in the practical sense of mission planning, but along trajectories that will bring them nearer to certain stars than to others. These encounters are not arrivals. The distances will still be vast, measured in fractions of light years rather than in close approaches. Even so, the imagination fastens on them because they convert cosmic drift into something like narrative. A silent machine from Earth may one distant day pass nearer to a star unknown to its builders. It may traverse regions of space where the sun is no brighter than other stars in the sky. It may remain intact long after mountains, languages, cities, and even species on Earth have changed beyond recognition. The mission therefore acquires a second life in thought, one no longer about data return but about duration. Duration creates another form of mystery. Space is not empty in the way popular images often imply. Over immense spans of time, surfaces are altered by cosmic rays, dust impacts, ultraviolet light, and the gradual effects of extreme thermal stability and instability. A silent spacecraft crossing interstellar space does not remain untouched. It is weathered by the galaxy, though on scales difficult to compare with any familiar erosion. Metal changes, insulation degrades, micrometeoroids strike. Yet because the environment is so sparse, destruction is slow. The Voyagers may outlast almost every structure currently standing on Earth. They may preserve traces of 20th century human manufacture long after those traces have become archaeologically inaccessible at home. This inversion is subtle and disturbing. The farthest human-made objects may become the longest-lasting witnesses to the age that launched them. The messages they continue to send while active are not only scientific in this light, they are evidence that connection can persist across almost unmanageable distance. Each recovered bit affirms that intention. Once translated into machinery, can survive years of cold, radiation, delay, and diminishing power. Of course, the connection is not emotional in itself. It is engineering, encoded radio, error correction, carrier tracking, thermal modeling, command sequences. Yet over time, the distinction between engineering and feeling becomes harder to keep absolute. A spacecraft that has taken decades to reach interstellar space and still answers when called, begins to attract forms of attachment that no mission planner can fully formalize. Concern over a glitch, relief at a restored transmission, fascination with an unexpected diagnostic pattern, all become part of the mission's human shadow. The machines are not alive, but their persistence invites the language of endurance more naturally than that of mere hardware. There is also a quiet irony in the way the mission ages. The farther outward it goes, the less likely it becomes that any new data it sends will transform public imagination the way the planetary encounters once did. No single particle count in interstellar space is likely to rival the first close image of Saturn's rings, or the discovery of volcanic plumes on Io in emotional force. Yet from a scientific point of view, these late measurements may be just as precious, because they sample a region no mission had previously reached. The problem is not their value, but their visibility. They require interpretation rather than immediate awe. This makes the late Voyager mission a study in hidden importance. It gathers some of its deepest insights in a form least suited to spectacle. Eventually the signal will stop, not because the spacecraft have reached a final destination, but because energy will fall below the threshold required for meaningful operation. There may be no dramatic final message, no ceremonial closing sentence. A subsystem will be disabled, or a transmitter will no longer be supportable, or thermal conditions will push some critical component beyond tolerance. The line will simply end, and Earth will continue listening for a while, partly from caution and partly from reluctance. Silence in deep space is always ambiguous at first. It could be a temporary fault, it could be geometry, it could be noise. Then, after enough time, silence will become fact. One by one, the Voyagers will cease to be speaking objects, but even then the larger message remains. Two machines built by a planetary species managed to cross the orbit of Neptune, pass through the vast declining wind of their parent star, and enter the medium between stars while still carrying evidence of their makers. They do not travel quickly enough to bridge the true interstellar gulf in any humanly useful way. They do not approach other suns as explorers in the dramatic sense. Yet they do something quieter and perhaps more revealing. They prove that a civilization rooted on one small planet can project its instruments, its records, and its patience far beyond the zone in which life itself evolved. The signal weakens, the power wanes, the language of telemetry grows sparse, but the act remains. A message travels through darkness long after almost every practical reason has dissolved, and still it goes on speaking for a while, thinly but undeniably, from a place where no human senses can follow. In that long persistence there is no final answer, only a slowly receding question about what it means to send anything at all into a universe so large that even success looks, from far enough away, like a whisper trying to remember its source. Once the Voyagers begin to move through interstellar space in the local physical sense, the imagination naturally turns ahead. The probes themselves are not going anywhere that can be called a rival within any human timescale. They're still far inside the greater gravitational outskirts of the solar system, and even their tremendous speed shrinks against the distance to the nearest stars. Yet something essential has changed. For the first time, a human-made object is no longer only exploring planets within the Sun's immediate domain. It is moving through the medium that lies between stellar systems. That fact draws the mind outward from the spacecraft to the stars themselves, to the nearest lights that have always hung above Earth as fixed points, though in reality each is a sun with its own motion, history, and perhaps its own surrounding worlds. The Voyagers do not reach those stars, but they force a new continuity into thought. The gap between planetary exploration and interstellar travel no longer feels entirely philosophical. It remains immense, but it has been entered. The nearest major destination in that widened imagination is Alpha Centauri, the closest stellar system to the Sun. It lies a little more than 4 light-years away, near enough to seem almost adjacent in galactic terms, and still so distant that Voyager, moving much faster than any previous outward-bound craft, would need tens of thousands of years to cover a comparable span. Alpha Centauri is not one star but a small family. 2 of its members, Alpha Centauri A and Alpha Centauri B, orbit one another in a long gravitational dance, while a third, Proxima Centauri, circles much farther out. From Earth, the 2 brighter stars appear as a close pair, sun-like yet not identical. One resembles the Sun enough to invite comparison, while the other is smaller and somewhat cooler. Their alternating distances from one another shape the environment around them and complicate the stability of orbits for planets that might circle too far from either star. Yet this complication does not erase possibility, it sharpens it. A nearby system with multiple stars feels less like a single target and more like a neighbouring territory full of zones, gradients, and differing prospects. Proxima Centauri, the dimmest and closest of the three, has drawn especially intense attention because planets are known to circle it. Proxima is a red dwarf, much smaller and fainter than the Sun, the most common kind of star in the galaxy, and also one of the most difficult for habitability in the simple sentimental sense. Red dwarfs burn slowly and can live for immense spans of time, yet many are active, prone to flares and magnetic violence. Proxima is one of these restless small stars. It sends out bursts of radiation and particles that may threaten any nearby planet with atmospheric erosion and harsh surface conditions. And yet one planet in particular, Proxima Centauri b, orbits within a range where liquid water could in principle exist if the right atmosphere is present. This combination of promise and hazard makes the system deeply compelling. A world may exist in the nominal habitable zone of the nearest star, and still that habitability may be fragile, perhaps temporary, perhaps impossible at the surface, perhaps preserved only under ice, underground, or not at all. Again the pattern returns. Every discovery enlarges the field of possibility and uncertainty at the same time. No telescope has yet delivered a direct, revealing portrait of that planet's surface. Its seas, if there are seas, remain unseen. Its sky, if it has a sky dense enough to soften the star's violent moods, remains unseen. Most of what is said about it arises from orbit, mass, probable composition, estimated temperature, and the behaviour of the parent star. Still, even this partial knowledge is enough to alter the emotional map of the cosmos. During most of human history, the nearest stars are only lights. Then they become suns. Then some become suns with planets. Then one of those planets lies in a region where water might exist. The change is incremental, careful, and incomplete. Yet it is profound. The nearest stellar system is no longer a bare abstraction. It has weather possibilities, atmospheric possibilities, geological possibilities. Its unknowns become textured. Other nearby stars add different shades to that texture. Barnard's star, a small red dwarf not much farther away, moves rapidly across the sky against the more distant background. A reminder that the stellar neighbourhood is not static but flowing. Evidence suggests a planet there as well, perhaps a cold super-Earth, likely too frigid at the surface for open oceans under ordinary expectations, yet still interesting because cold worlds are not simple worlds. If large enough, if internally warm enough, if buried beneath thick ice or insulating material, such planets may host hidden liquid layers. Sirius, brighter and more visually dominant in Earth's sky, offers almost the opposite image, a brilliant binary system with a luminous main star and a white dwarf companion, a place of spectacular stellar history and likely severe environmental instability for planetary formation near its more dramatic phases. Wolf systems and other nearby red dwarfs present their own arrangements of rocky worlds, some perhaps within temperate ranges, some clearly too hot or too cold, each one reminding astronomy that the neighbourhood around the Sun is not composed of a few empty lanterns but of many differing environments. This matters because the Voyagers, though not headed toward a useful arrival, become part of the same mental geography. They are not moving at anything like the speed required to make the nearest stars accessible in a civilizationally manageable way. Even light itself needs years to make the crossing, and the Voyagers move at a tiny fraction of light speed, yet they define the beginning of a path rather than its completion. They show that spacecraft can survive beyond the planets, can communicate across immense distances, can carry instruments and encoded cultural traces into interstellar space, and can keep working after every visible landmark has fallen behind. In this sense, they do not solve interstellar travel. They make it harder to dismiss as pure fantasy. The road remains too long for current methods, but a road is not the same thing as a wall. That distinction helps explain why later concepts for interstellar flight often sound both bold and strangely modest. One of the most discussed is the idea of sending extremely small probes to the Alpha Centauri system using powerful lasers to drive light sails. The craft in such a concept would not be large, protected vessels carrying humans or even heavy laboratories. They would be miniature instruments, accelerated to a significant fraction of the speed of light by Earth-based energy systems, reaching another star within decades rather than millennia. The proposal is difficult on nearly every front. Materials would need to survive intense acceleration and interstellar dust impacts. Navigation would need precision at a scale almost beyond precedent. Communication back to Earth would be extraordinarily challenging from such distance with such tiny craft. Yet the concept persists because physics does not completely forbid it. It narrows the problem from impossibility to severe engineering, and that narrowing owes something, however indirectly, to the precedent Voyager establishes. The old question asks whether anything made on Earth can leave the planetary system and go on functioning. The Voyagers answer yes. The next question asks how much faster, lighter, and more resilient such craft might become. Still, speed alone does not settle the deeper mystery. A probe reaching another star system would not necessarily answer the questions that have gathered around nearby planets. A world in the habitable zone may be sterile. A world outside it may hide a deep ocean. A dense atmosphere may preserve warmth or trap lethal chemistry. A magnetic field may shield life or fail to develop. Stellar flares may strip air or simply shape its upper layers. Every hopeful sign carries its own counterweight. Even on Earth, life leaves subtle signatures that could be difficult to read from afar. Around another star, with sparse data and long delays, the problem becomes more difficult still. The nearer stars are close enough to attract plans and far enough to protect their mysteries. There is also the matter of time, which the Voyagers teach in an especially severe way. On human scales, the nearest stars are remote. On cosmic scales, they are neighbours constantly changing their relative positions over tens of thousands of years. Proxima draws nearer for a while, then will drift farther away. Barnard's star moves through the sky with noticeable haste because of its proximity and true motion. The stellar neighbourhood around the Sun is not a static map but a slow current. A probe launch now toward one destination moves into a future sky in which the arrangement of nearby stars will not be quite the same as when it departed. Over the millennia required by slow craft, even neighbourhood becomes a moving target. This lends interstellar planning a peculiar instability. The destination is real, but the context of the destination will continue to evolve throughout the journey. The Voyagers themselves will eventually pass comparatively nearer to certain stars than to others, though never near in the ordinary sense of mission arrival. These remote future approaches often inspire attention, because they provide a way to imagine the probes continuing after all contact is lost. Voyager 1 may, in tens of thousands of years, pass within a modest fraction of a light year of a particular star. Voyager 2 will have its own distant stellar passages on even longer timescales. Such events are not encounters in any practical way. The stars will not be visited, only passed at distances still immense beyond ordinary reckoning. Yet the thought matters because it reveals how deep time transforms even a drifting artifact into part of the larger galactic movement. The spacecraft are not simply escaping the solar system. They are joining the circulation of the local stellar environment. This is where the journey becomes quietest and widest at once. The planets are behind. The sun is becoming one star among many, still brighter than the rest from the probe's perspective for a long while, yet no longer the unquestioned centre of every surrounding process. Ahead lie stars with planets, stars without planets, stars that flare, stars that cool, stars that have already passed through more dramatic stages than the sun has yet known. Some nearby systems may host rocky worlds with skies and weather. Some may hold frozen super-Earths, hidden oceans, or barren stone. Some may have endured catastrophic early histories that stripped away any calm surface long before complex chemistry could settle. In every case, the closer astronomy looks, the less likely it seems that one simple model of habitability or lifelessness will be enough. The Voyagers therefore end not by closing a story, but by widening its frame until the original mission begins to look like a preface. They leave Earth to exploit a rare alignment of giant planets. They reveal storms, rings, volcanic moons, hidden oceans, strange magnetic fields, and the shape of the sun's outward pressure against the galaxy. Then, by continuing beyond all intended dramatic encounters, they make the next scale unavoidable. The solar system is not an isolated gallery of worlds complete in itself. It is one local expression of processes that almost certainly repeat in altered forms elsewhere. A moon hidden beneath ice at Saturn suggests that oceans need not depend on sunlight. A methane world at Titan suggests that atmospheres and chemistry may organize themselves in unexpected ways. A volcanically tormented Io suggests that orbital dynamics can transform a small world into a furnace. Each of these lessons matters when the mind turns to exoplanets. It becomes harder to assume that a distant planet's meaning can be guessed from position alone. Worlds may be reshaped by tides, atmospheres, impacts, internal heat, capture histories, and hidden water. The solar system, studied outward by Voyager, becomes a caution against simplicity when reading the stars, and still the oldest mystery remains untouched in any direct sense. No sign of life has been found by Voyager. No message has arrived from elsewhere. No nearby exoplanet has yielded a visible coast or cloud-shadowed sea under another sun. The spacecraft travel into the medium between stars carrying evidence only of their makers, not of any others. Yet their silence on that question is not emptiness. It is context. They demonstrate how much can exist beyond first expectation. Volcanoes where cold had been assumed, oceans under ice, atmospheres where a moon should have been bare, boundaries in space where a star's influence weakens gradually instead of ending cleanly. If the known universe of the sun contains so many revisions of expectation, then the nearby stars may well do the same on an even larger scale. The absence of conclusion becomes, in this light, not disappointment, but discipline. Far ahead, the probes will continue on, dark eventually, then colder, then silent forever, carrying their records through a stellar neighborhood that is itself slowly changing. They will not answer the great questions about nearby worlds. They will only keep them open. Their true destination is not Alpha Centauri or any other named star. It is the widening region of thought in which the nearest stars cease to be ornaments and become possible places. The first crossing has barely begun, and already it has shown that between the sun and the next lights there is not a void of nothing, but a medium, a frontier, and a length of time large enough to humble every quick conclusion. The Voyagers continue outward without urgency, and that may be the quietest part of their story. They no longer move from spectacle to spectacle. No giant planet waits ahead. No hidden moon rises suddenly into view. The great encounters are behind them now. Yet the sense of wonder does not fade with the light. It changes its form. It becomes slower, thinner, and more difficult to name. The spacecraft pass through a darkness that is not empty. carrying the last faint warmth of their own power and the long memory of the system that made them. Around them, interstellar space remains sparse and cold, but not still. Particles drift, magnetic fields lean through the medium. Distant stars hold their positions only in appearance, while in reality each one moves through the galaxy on its own long path. Far behind, the sun continues to shine, though to the Voyagers it has already begun to look less like a home and more like one star among others. Earth is smaller still, far beyond sight, existing only as the place that once built these machines and sent them outward with more hope than certainty. The golden records remain fastened to their sides, unchanged, unread, and patient. Perhaps they will never be found. Perhaps they were never truly meant to be found. Perhaps their deeper purpose is simply to exist, to declare that a brief and curious species once looked into the dark and chose not only to measure it, but to leave something of itself within it. Nothing in this journey ends cleanly. The edge of the heliosphere is not a sharp border. The nearest stars are not simple destinations. Even silence, when it finally comes, will not be a true ending. It will only mark the point where the machines stop speaking and continue drifting. Beyond them, the galaxy remains full of worlds not yet seen closely, oceans not yet confirmed, atmospheres not yet understood, and patterns that may once again overturn whatever seems certain now. The Voyagers move on through that unfinished distance, and the mystery ahead remains larger than the path already crossed.